Hello guys, welcome to my YouTube channel once again. Cdacc Structure Hub. This is a place where you learn, build and innovate. So today I want to talk about beams subjected to a couple moments. Guys, sometimes a beam is subjected to a clockwise moment or anti-clockwise moment or a couple at section. In such a case, the magnitude of the moment is considered while calculating the reaction. For example, as you can see on my beam on the whiteboard, we have this moment which is moving in anti-clockwise direction, and the magnitude is 65 kilonewton meter. So the bending moment at the section of the couple changes suddenly in magnitude equal to that of the couple. This may also be found out by calculating the bending moment separately with the help of both reaction, since the bending moment does not involve any load. Therefore, the shear force does not change at the section of the couple. So, as you can see here, this is the moment, the anti-clockwise moment. So, the shear force at this point, at this section, will not change. So, while you will be drawing the shear force diagram, where at a section of the beam where it is subjected to a moment like this, it will not affect the shear force diagram. So, in regard to that, I want to analyze a question from Cdacc paper. So that is Cdacc 2024 November, question number 9. So the questions reads, analyze the beam and determine its support reaction. Hence draw shear force and the bending moment diagrams and indicate all critical values. So this is the beam, guys. As you can see, is subjected to a anti-clockwise moment with a magnitude of 65 kilonewton meter. So again, we have a UDL, uniform distributed load, of 70 kilonewton meter, spanning at 5 meter. So let's see how you can handle such a question. So the first thing to do, as usual, you extend this line to give you space to draw shear force and the bending moment diagrams. Like that. And then, after that, the next thing is to start calculating the reaction. As you can see, this is a statically determinate beam. So we will use the 3 equations of equilibrium. Number 1 of the equation, the summation of moment about a point is equal to 0. And number 2, the summation of horizontal forces should give you 0. And the summation of vertical forces should also give you 0. So let's begin by summing moment about a point. So summation of moment at A should give you 0. Not at A, because there is not a support at B, should give you 0. So when you sum moment at B, automatically what you will be looking for is the reaction at C. So we said that all the forces that moves or that will be moving in clockwise direction will be considered as positive, and those that will be moving in anti-clockwise direction will be considered as negative. So our point of reference is B. So in which direction is reaction C moving in reference to point B? So you are here at C, so it will be moving like this. So that is anti-clockwise direction. So it will be minus RC times the distance from B to C. That is 1 plus 5, 6. So moment is the force times perpendicular distance. After that, we will come to a moment which is 65 kilonewton meter. As we said earlier, this moment will be considered or will be used in calculating the reaction. So the moment is moving in anti-clockwise direction. So you will minus 65. So this 65 is already a moment. So there is no need of multiplying by the distance, which is 2 meters. So you just take it the way it is, 65, and subtract it. And then we have a UDL of 70 kilonewton per meter. So a UDL, you will first convert this UDL to a point load by multiplying the distance covered by that UDL. So in which direction is that UDL moving in reference to point B? So this UDL, it starts here and it ends here. So that is clockwise direction. So that one is plus 70 times 5. By doing so, you have converted a UDL to a point load. Then the bending moment for UDL, it acts at the center of that beam. So times 5 over 2 plus 1, like that. Is there any other force? No. So you will equate it to 0. And then you simplify by opening the bracket. So we have minus 6 RC minus 65 plus take your calculator. So we have 2.5 plus 1 times 5 times 70. So it's 1225 plus 1225 should give you 0 minus 6 RC and then you do the operation here. That is 1160 plus 1160 should give you 0. When minus RC, it crosses to the other side, changes sign from negative to positive. So we have 6 RC should give you 1160, which imply RC equals to RC equals to 193.33 kilonewton. So we have calculated reaction at C. We know that summation of upward forces should be equal to summation of downward forces. Upward forces is reaction at B plus reaction at C. This one should give you 70 times 5, like that. So this is a moment. So when you are using when using this this equation, you should not consider the moment, because this is a moment. It's not a force. So summation of upward forces should be equal to summation of downward forces. So do not use moment. So we have RC plus 193.33 should give you 350, which imply RB equals to 350 minus 193.33. So this one will be, punch your calculator. So 156.67. 156.67 kilonewton. Again, a point to note, the reaction at B, you can also calculate reaction at B by summing moment at C. So now let's now draw the shear force diagram. So to draw a shear force diagram, first draw a baseline. That is shear force diagram. And you start plotting your values. So as you can see, this section from here to here, there is no force. So it is you'll draw a straight a line, a thick line up to there to show it is a zero shear force. So just draw a thick line like that, and then after doing so, you'll come to reaction at B. Reaction at B is 156.67. So you approximate where 156.67 0.67 is. So let's say it's somewhere like there, like that. So give it a value, 156.67. And then it will be constant. It will maintain constant up to the next loading, which is a UDL. So 156.67 minus 156.67 minus 70 times 5, which is 350. So you get a negative 193.33. So it's negative 193.33. So somewhere like here. Let's approximate. So you draw a diagonal line. So 193.33. And then negative 193.33 plus RC. So it will be 0. So you go back to 0. 0. So this is plus, minus. Like that. And your shear force diagram is complete. The next thing to do is to calculate the bending moment. And how do you calculate the bending moment? So bending moment. So bending moment at C is equal to 0. Bending moment at C is equal to 0. And bending moment at A, bending moment at A equals to minus 65 kilonewton meter. Why minus 65 kilonewton meter? Because a beam is subjected to a moment which is moving in anti-clockwise direction. As you can see, at point A we have 65 kilonewton meter. So bending moment at B it will be also minus 65 kilonewton meter, because at this section, this bending moment or a moment which is moving in anti-clockwise direction, it has affected at both point A and B. So at B, it will maintain minus 65 kilonewton meter. Bending moment at D, it will be bending moment at B plus the area of this shape, which is a rectangle, so it will be 156.67 times 1. So we'll have 60 minus 65 plus 156.67. So this one will be minus 65 that is 91.67 kilonewton meter. So let's now go to this part. So we have this let's call here y, where the shear force is changing sign from positive to negative. That is where we'll have our maximum bending moment. So before you calculate bending moment at this point, you will have to find distance x and also this distance. So this will be 5 minus x. So using similar triangles, you can say that x over, this is x from here to here, and then here to here, 156.67 should give you 5 minus x over this distance from here to here, 193.33. So you can cross multiply. So we have 193.33x should give you 156.67 into bracket 5 minus x, which imply x equals to, I hope you can find the value of x. So 24 meters. So that is the value of x. And then here it will be 2.76. So bending moment at y. Bending moment at y. So bending moment at y, it will be bending moment at D plus the area of this rectangle. So it will be a half times 2.24 times this distance from here to here, height 156.67. So this one will be 91.67 plus, take your calculator, So 175, 175.47. So this one will be 267.14 kilonewton meter. So that is our bending moment at Y, which is the maximum bending moment. Yes, like that. Then after doing so, now we can plot our shear force diagram. So no, our bending moment diagram. So this is the bending moment diagram. Bending moment diagram. So at point A, we have negative 65. So somewhere like there. 65, so it will be constant up to point B, because B is also negative 65. And then at D, we have 91.67. So 91, let's approximate around there. So it will be a diagonal line. 91.67. Then at Y, 267.14, somewhere like there. So 267.14. So this one will be a curve, a smooth curve. And then at C is 0. At C is 0, so it will be also a smooth curve. So this is minus, this is plus.